Test. Yeah, okay. Ready to get going? Okay. A couple of people asked me after the last session where they could read more about Bootstrap and about false discovery rate. And I think that was a nice opportunity to mention Brad Efron's name. Brad is a professor at Stanford, has been a leading statistical thinker for many, many years. I find every time I read his papers, I learn something. So just go read some of Brad's papers, and I think you'll get a lot out of them. So in particular, he has a book called Large Scale Inference. And by large scale there, he means dimension, not number of data points. And the FDR picture is presented there. He did develop it, but he brought some real insight into it. And in particular, one way to think about FDR is that you start off as a Bayesian. And this is often the case that a Bayesian framework gives you kind of a clean way of thinking about the problem. It's sort of, in some sense, the right way to do it if you could. So he says, well, I have multiple decisions to be made. I want to have the error on all those decisions controlled, and that's a Bayesian error. Okay? It's a typical thing of the probability that you the null hypothesis was true. Okay, this is now done in the multi-decision setting. So that's a Bayesian statement, and the frequentists turn that around. So he says, let's start with the Bayesian framework, and he writes down the right Bayesian posterior to control the overall probability of making a bad decision in a set of decisions. And then at some point, there's a term in the denominator which he doesn't know. You'd have to have a prior in there. If you put in a prior in there, you just get, in some sense, an arbitrary result. If you knew the prior, quote unquote, you would know the right thing to be. You don't. You know, problems where you have 100,000 decisions to make, just don't know that number. So he, at that point, goes to what's called empirical Bayes. He finds an unbiased estimator for that quantity. So he's now left Bayesian behind, and he's done something else. And so now he needs a new justification that this is the right thing to do. So now he starts to do frequentist theory of the kind that we're all used to, and justifies this thing, in fact, controls the FDR, and does the math for that. So I think that, I tend to blend Bayesian and frequentist style in my thinking. I think most statisticians do. And this particular book is a really good way to see that blend happening. And it sort of explains why FDR has this particular form, and explains how to do the theory of that. And I think in lots of other problems, it's very useful to think in terms of Bayesian in the beginning. So shrinkage. If I have a big hierarchy of models and they're all related in some way, I want them to shrink towards each other. I can write that down as a Bayesian model. And then at some point, there's a prior I might be uncomfortable putting on the system. I can estimate that quantity, maximum likelihood, get things like James-Stiles shrinkage. So that's one thing to read. And then Brad also is the developer of the Bootstrap, and there's a book by Efron and Tibshirani, which is a very easy read. Just little short chapters on estimate. So what's the Bootstrap estimate of variance? Kind of very natural. What's the Bootstrap estimate of bias? And just kind of going through that. It's a thing you can read in a kind of a long weekend, and just kind of learn about that style of thinking. Which I always like to try to emphasize. I think it's really important. Resampling perspectives on inference. Okay, any further follow-up from the inferential topics of this morning? Okay, so we're going to be back to sort of more optimization and less inferential material now. I promised something that was not mathy. So I've picked about 5 different little subtopics, and we'll sort of see how these go. And each one of these will be relatively short. This one is just some brand new work that is being done in my group at Berkeley. And it reflects the systems side of my personality, which is only developed over the last 10 years. But I really believe in this. It's my daughter calling me. Say I'm sorry. Again, kind of to belabor this a little bit, but people now are using the word AI for everything, and machine learning. Let's turn this off. Whereas it's mostly machine learning under the hood. So I think of machine learning as this broader thing, and I think of it mostly as statistics, but it spills into control theory and optimization theory. And anytime you build a big system that interacts with the world, like a transportation network or a finance network, you have to do some machine learning or statistics. You have to calibrate, and you have to collect data, and so on and so forth. I don't think of those as classically AI problems. I think of those as systems problems. So to do them right, you first of all have to get the math right and the statistics right, and so on. And you also have to work with real systems builders, people who do that as a living. who build robust, reliable software, people who build the oracles of the world and who build real software that really works at scale. So about 10 years ago, I decided to really invest in becoming that kind of researcher, and so we started a lab. Actually, it was one before the AMP lab. It was called the RAD lab. So that was 5 years, and the AMP lab was 5 years. And this was the AMP lab. It ended this year, but it was Mike Franklin, a colleague, who's a database researcher, Jan Stoika, distributed systems researcher, and me, bringing the math stuff. And we aimed at building a data analysis stack that had statistical principles informing it, in particular things like error bars everywhere and scalability issues taken as first-class citizens. So a lot of software came out of this lab, and some of it is really world-leading. So Spark is the most famous one. That wasn't developed by my group. That was really Matej Zaharia, who was a student there, and then Jan Stoika advised that project. But it was driven by the students in my group complaining about MapReduce and Hadoop, which would take in data, do a mapping to high parallelism, then reduce it back down, but that would be the end of everything. And machine learning workloads iterate. And so they said, well, every time I run MapReduce, it'll block while it goes and gets the new data, again off the disk. And so Matej said, well, I can help you with that. I will build a caching version of Hadoop, which doesn't make you go back out to the disk. And that is what is called Spark. It's a sort of a smart systems builder way to think about caching of all the data so you can iterate. I'll tell you about Cocoa today. That was developed in my group. It's a state-of-the-art distributed optimization and learning system that's being used in industry. I told you this morning about Bag of Little Bootstraps. This was driven by trying to work with Jan and others on a database that took in a query and gave out an answer with an error bar around it all the time. And there was a follow-up to that after the Bag of Little Bootstrap idea was developed, was to how also do diagnostics. That all error bars can be wrong, and you'd like to have some idea that they're wrong. Make assumptions and say they'll never be wrong, but it's not the life. So you have to worry about diagnostics. And that's another theme that hasn't come up much in the machine learning community, is you make certain assumptions, or say you're making no assumptions, and you run your algorithm, and that's it. Here you present the results. Well, lots of times your assumptions aren't actually true. You made an IID assumption or something like that. And you would like to be able to sort of look at the answer of what you got and do some sanity checks on it and say, there's something not quite what I expected here. Those are called diagnostics. So you may have heard about them in linear regression. In linear regression, you will fit a line through the data, and then you will take all your residuals, and then you'll do what's called a QQ plot. You'll plot those against the normal quantiles, and they should follow in a straight line or a diagonal line. Okay? Now that's not part of your modeling assumption. That's a after-the-fact check. If they don't follow the dotted line, that doesn't mean you know how to correct your model. It just means that something went wrong. So you better step back and think about what's part of your assumptions you did. So you need diagnostics for everything. Clustering algorithms should have it, regression should have it, classification should have it too, and we need to work. So we did that for error bar stuff. And I won't tell you about some of these other projects. Cyclades is a very interesting one if you're interested. It's kind of a graph theoretic approach to doing parallelism and multiprocessor, but not distributed set. Recent stuff. So anyway, as this developed, my students were mostly doing all this theory kind of stuff I've been talking about here. But they got a little bit jealous of how important and famous Spark became. It's probably the most widely used data analysis platform there is right now. And sort of said, well, why can't we contribute? Why does the systems people get all the credit? So this new lab is called the RISE lab. It just started in January. It's some of the same cast of characters. And we're trying to make this into more of less of a batch data setting and more into a real-time, guarantees about runtime that also fresh, updated kind of systems. So some of these things, it's a systems project, so it's sort of in sometimes the best ideas are the simplest ones from our point of view, but the systems be able to make them real and scalable and robust, that's kind of interesting things have to happen, okay? So we're targeting things where you have to have a lot of flexibility. So if you look at something like AlphaGo, it's not just a neural net. In fact, it's quite not just a neural net. It's a Monte Carlo tree search together with all kinds of other things that make it actually do something. So you got to bring together neural nets. Planning also is not talked about enough. In AI, it's one of the other areas that's reasonably successful. And then if you're going to do reinforcement learning kind of things, you have to be able to prepare to do lots of search and lots of simulation. That's not just part of build a neural net with TensorFlow. It's other stuff you need to bring together. And you need all kinds of dependencies among all these pieces. They're going to be very fine-grained. It's not enough just to do map reduce, parallelize in a dumb way, and then bring it back together. And then very importantly, you want to be able to adapt the data flow based on the task progress. Most of the map-reduce paradigm is something you know a priori. I'm going to map and reduce in a certain way, and I just repeat that process. So I program it in. But in lots of situations, the connections between the pieces emerge as the thing runs. And then we want to do this in kind of real-time situations. We're working with roboticists and others where kind of home robots need to interact in more or less real time. Okay, so here's a little cartoon of what we've actually built. So this is an existing system. I'm going to show you a GitHub address later. It's an open source project. You're certainly welcome to join in and help with this. It will require a big community to make it really real. But the kind of cartoon picture is that it's more of a data flow kind of architecture. So here's Hadoop or MapReduce. It would break problems into lots of tasks, and then the tasks would run in parallel, and then there would be a synchronization barrier where you'd wait for all of them to complete, and then you would do a reduce step, and then that whole thing would continue, right? Well, in problems like, I'm going to show you a little reinforcement learning exercise later where you're trying lots of, you have a policy, you're doing rollouts, so you tried some branch of the policy, and maybe it's like a robot running, and so you go down that branch and it immediately falls over. Right, but in parallel, you'd like to try all kinds of other branches. So in parallel, you try some other branch where it actually stays up for a long time, and that difference in time can be like factor 10 or 100, right? So in this classical paradigm, you do this all in parallel. That's great, but this thread would be waiting forever for that thread to finish, and so you don't want that to happen. You want as soon as one of them has fallen down for some other machinery to come into play, start to do another simulation. Okay, so something more like this. So this is kind of a data flow architecture. Things like this have been studied, in computer science for a long, long time. But to do this in the MapReduce style, where there's like 100,000 servers, and some of them could be broken, and there's those lags, there's stragglers, and so on and so forth. That is the problem. So let me show the two students who've led this. One of them is from Germany, Philipp Moritz. I don't know, maybe some of you know Philipp. And then Robert Nishihara is the other one. And they've spent really 2 years of their life doing this, even though they're theoretical machine learning people. They've proved theorems in previous papers that are quite impressive. They decided they would really take this seriously, and they spend all their day, every day, hacking away. And so this project is called RAY. It aims at latency, control of latency, and as I mentioned, this heterogeneous task. In particular, it supports CPUs and GPUs, and it allows very fine-grained task dependencies, not just big blocks of things being done. Data flow can depend on task project progress, and there's kind of a general actor formalism that allows that to happen. And you're able to share lots of state so that tasks would coordinate in various ways. And then the kind of usual things you would like to be able to achieve in any large-scale distributed system. So here's a little bit of again, somewhat of a cartoon, which just gives you a little bit of flavor of this system. It has a lot of attention to scheduling. So there are local nodes which are distributed. They do not share memory. Locally, they'll share memory among threads, and there's a scheduler there, and that schedule will interact with a global scheduler. There's also a lot of attention to where objects are stored so that there's a coherence overall, and you don't have to send very much data back and forth. So there are local object stores, and there's a global object store. So, there's a paper has been written about this if you're interested in all the details, but just to say that it's sort of been 2 years of worrying about the scheduler and about the way to share objects. All right, so I'm going to just show you one little bit of code here and then an actual result of running this system so that I can claim that it actually exists. There's several little examples we had. I'm just going to pick one that's most relevant to people here. It's a reinforcement learning task. And let me show you the actual code that runs to do it. So this looks to a user like Python. It is just Python with a little bit of extra annotation to it. So the user has to think not at all about a distributed system, as has been the goal. And so here is this little thing. It is a simulation-based reinforcement learning architecture. It's going to simulate a humanoid robot with arms, legs, muscles, and so on. The control signals are control to the muscles. And it will basically just do a little kind of simulator. So just Python. The purple stuff up there is the Ray part. You tell this, you have a little decorator that says this piece of code is going to be done remotely. Be prepared to send that out to multiple simulators and run them in parallel. Okay. And then behind the scenes, all of the Ray sets all up of the parallelism and so on. So then when you actually run this thing using that simulation object, then you would do this. You would create a whole bunch of trajectories. There's this operator here that creates the parallelism. and then you would update your policy. Whenever the thing finishes, this thing returns, so there's no blocking, and you update the policy asynchronously. All right, so that's how you use this system. And I think on the next slide, I actually had a simulation running. Let's see if this is actually, yeah. Okay, so this is let me just say, this is a standard. It's something, these days, kind of reinforcement learning starting to come back, but it's still hard. I don't think that AlphaGo is all that indicative. Mostly it's being done with policy gradient kind of methods. You do rollouts. You just try all kinds of control paths, and then you get answers, and you back them up in a policy. This one is this is MuJoCo. It was done by Amo Todorov at the University of Washington, another ex-student of mine. And he developed a really good humanoid simulator that includes, bones and kinematics and dynamics and muscles. So imagine yourself having about 45 little degrees of freedom, little strings you can pull on, and your goal is to pull those strings in such a way so this robot stands up and starts to run. All right, so it's much harder than like a marionette with like 5 strings, but also you're pulling on the muscles. You're not actually pulling literally on the pieces of the body. So it's a pretty decent, challenging problem. And you'd like to have this thing learn in something less than 1 billion steps. Because after 1 billion steps, sure, you've explored everything. You'd like to have it learn more quickly. So this is a good example of something, now at this point it's just an experimental result. Can we get this thing to start to run so we can do all kinds of experiments relatively quickly? And so you'll see this whole thing is running in basically real time on Ray. Oops, there was the... So here we are at iteration 20. It's not even learned to stand up yet, but it's kind of starting to get a little bit of control over its body. There's iteration 80. It's starting to move forward a little bit. And iteration 100 is kind of jittering. And so the reinforcement learning signal here is just the more you move to the right, the better that is. Nothing else. No other apprentice, anything. All right, so it has discovered a gate at this point. And at iteration 500, it is now running. Now it's running in a slightly odd way. It's got its arms flayed out behind itself, but it is been seen run. Okay, so this is the kind of thing you might now think about using if you're Technicolor or something inside of a graphics package where you're trying to create avatars that run around in some world. Currently, artists are having to kind of do all that by hand. You have hundreds of artists on a film, and so because it's one of the problems is to do this in a real way that looks real is kind of hard. So at about iteration 1,000, those arms come back in, and it starts to look more feasible for that. So there, I'm not above showing some kind of AI-like results and get people to laugh a little bit. But it's just an empirical demonstration of an architecture. The main slide I want to show is this one, which is a GitHub project, and it is something that I think can be used in place of Spark. It's kind of ready to go on a large-scale machine learning problems. It targets not just batch, classical big neural net kind of problems or whatever. It targets the wider range of problems that we're starting to see emerging. And we really would love to get people elsewhere involved in this project. And I think just like Linux or whatever, I think that projects like this, it has a good chance of being, having seen Spark become as important as it was with much less. It's just a caching system. This has already quite a bit more in it. It's just a fun community-wide project. Okay, any questions about that? That was really, again, just kind of some advertisement for a project. There's a lot under the hood, which I did want to talk about. All right. Okay, so let me do let's see, that was all I wanted for that. Part 2 of my presentation here. This is some work on distributed optimization and learning. Okay, so we haven't talked about that at all, even though in the MLS schedule, I was listed as talking about distributed optimization for all my talks, and so I figured I'd better do something that has that flavor. Okay, so that distributed word is really important. It is hard to achieve, so lots of fields have worked on distributed control, distributed estimation, so on, with not much success over a large periods of time. It's hard to do. So, I think in our field, we've started to have more success on it. So just to be clear, distributed means that I'm on different processors that aren't sharing any memory, and they're linked by a commodity network. Right? Parallel generally means that it's multi-processors all on a shared memory. Okay, so very different paradigm. Shared memory, I can keep writing, and having overwrites, and I have to worry about asynchrony and so on, but I don't have to worry about communication. right? So now we're in the situation where we're on a network. We have to worry a great deal about communication, and that's going to be the key. It's to be communication efficient. And this is partly motivated by a colleague, Jim Dimmel, who's a numerical linear algebraist, and he worked on kind of the previous generation of large-scale numerical linear algebra. So BLAST libraries, he had a big role in that, and so on. So those guys, of course, kind of worked out how to do, like, calculate many eigenvectors at scale and how to do Gaussian elimination at scale and so on. The early algorithms were just kind of algorithms. There was no consideration of the actual underlying machine. And then BLAST worried about cache locality and the memory hierarchy. Okay, but then what Jim did in the last 10 years, him and his group, was to say, forget all that stuff. The real key is that when we have multiple processors that are separated by network, we can't send information back and forth across the network. That will kill us. It's communication, which is the big barrier. So they wrote a whole new suite of algorithms called communication avoiding linear algebra, which has revolutionized both dense and sparse linear algebra. A whole new libraries about this and that. So one wants to take that seriously, avoid communication. Okay, so there's been a fair amount of work where if you see people distributing things, and that's good, they get naive parallelism, but every time there's a synchronization step, if you have to send massive amounts of parameter vectors around or data around, it's not going to work. It's going to be it's not going to give you the speed ups you might have. So this is a project involving a whole large number of people. Martin Jaggi and Thomas Hoffman here just south of us, and Peter and others from UK, and then Ginger Smith in my group has been leading work here. So this is called COCO. So this is going to be more restrictive. We're back to the convex domain. This is work convex. And one can think about non-convex, but this is focused on convex. So let's think about kind of these separable convex cases where we have a F plus G kind of situation, you know, a regularized loss sort of setup. Okay, so you'll all sort of see. So how do we solve these? We use gradient-based methods nowadays. Gradient, and we go down here. All right, when things get big, how do you deal with this? Well, first of all, you can use iterative methods, you can use first-order methods, and you can use stochastic methods. So we've kind of learned to put all these things together and keep things small in N and relatively small in D as well. Okay, so here's the stochastic methods. They look at, as we talked about this morning, with SCSG at just a single point instead of computing a full data. Okay, so we're able to get rid of the N dependence in principle with stochastic methods. All right, but now if we go to parallel distributed, we have to worry about the D dependence, and the N dependence is going to come back and hit us. So let's think about this. So kind of a couple of cartoons of how to think about distributed optimization. One of them is you put all your data on different machines, and then you just do something stochastic. You know, sequentially, you look at on each one of the machines at one data point, and you immediately make a small change to W, the weight vector. You send all that, and you immediately change. So everybody stays more or less synchronized, and you don't get out of date. You don't get where one processor is working in one part of the parameter space and another one in a different part, and pull them together, you average, and that's not the right thing. All right, but the communication is going to be really, really high here. It's going to be sending updates, parameter vectors very long, frequently, and this will grind to a halt. All right, so we don't have any to worry too much about the convergence guarantee. It's just doing SGD, but communication issue. All right, the other way you can go is to really never communicate. You just locally just keep iterating through your data as you standardly do, and keep moving the parameter vector in better and better direction. Now you do that independently, but now how do you aggregate? So it's not at all clear how to aggregate. If you aggregate in a naive way, you may not converge. Okay? All right, so you'd like to do something a little bit more in the middle, and I think mini batch has been what many, many people have agreed is kind of the way to go. But now the devil's in the details. How big should your mini batch be? If it has to be too big, that's not going to help you very much. If it's too small, you have to communicate a lot. So it's all about trade-offs. It's all about system design and trade-offs. So a mini batch is, of course, you take a little small subset, and perhaps you iterate or not, and then you update. So this has got to be the right middle ground, and really the devil's in the details. How do we expose the relevant trade-offs and try to figure out the right things? Okay, so just naive mini batch is mostly been worked on in the stochastic gradient descent context. It also, the mini batches have to be fairly big, and you have synchronization difficulties to worry about. And then there's a need to average over the batch size, and averaging hurts you in this world. Averaging slows you down. And so can we get rid of these things And so this project aimed at trying to get rid of all three of them. It so went beyond SGD with the Primal-Dual Framework. It's not wildly beyond SGD, but somewhat beyond. And then there's a special decoupling that happens. The core of this idea is basically an extra little upper bound in the dual problem. And that extra little upper bound is critical. That's what allows you to take the local, on the local machine, you can immediately apply updates and you still don't get unsynchronized. You get a little bit, but you're able to control that. And the local operations are averaging over something much smaller than the batch size, so the slowdown you get from that is not going to happen. Okay, so what is this setting? It is a primal dual setting. There's the kind of primal problem we've written down before, and I hope that most of you know how then to turn this into a dual problem. Use what's called Fenchel duality. I think I saw Sue Reed's slides had something about Fenchel duality. This is a little different than kind of linear programming duality, and it's related, but it's kind of a broader tool that you should use in this field, like variational methods use it, and so on. So what you do basically is you take that L function, you form its Fenchel conjugate, and you dualize this, and you come up with what should be somewhat of a familiar sort of dual problem, where instead of W, which is the primal variable, the weight vector, you get this alpha variable, and you get an overall, the A is the matrix whose rows are the X's, and then we get the Fenchel conjugate L star appearing there. And so we've gotten, as many people have observed, a decoupling. Instead of having L of a coupled, all the W parameters are getting coupled over here by that L of the W transpose Xi. Here, all the alpha i's are appearing separately in that function. So that means in the dual, things are a little more box-like and a little more decoupled, right? So methods like ADMM exploit this. This is kind of a common strategy for the dual. So early support vector machine things had these kind of style of things in them as well. All right. If you simply, however, naively go to the dual and parallelize, you don't get big things, right? So we're going to have to go to this extra step of an extra upper bound. So, okay, so there is our global objective. Let's just look at it again. It's got these Fenchel conjugates of our loss function, and it's got a norm of a linear operator. And what we're going to do is work out a local objective that each machine is going to use. On the kth machine, I'm going to have a subset of the dual variables, and I am going to optimize only over those, right? And so I don't want to, after my 4.5 hours of lectures, I don't want to spend too much time on mathematical details. You can look in the paper. If you add all of these things up, that gives you an upper bound on this quantity here. So by going downhill on this, you are effectively going down an upper bound on the quantity above. Okay, so that is our little upper bound. It's kind of based on a kind of a quadratic estimating function technology. All right, so what we're going to do is indeed solve this problem, maximize that, using any internal optimization method on the separate machine. So if you prefer stochastic coordinate descent, that's fine. If you prefer stochastic gradient, if you prefer Adagrad, fine. All of those are fine. You can do that on your local machine. Then we're going to do an immediate application of local updates. Instead of waiting to the end of the loop and then adjusting W, we're going to be able to do that immediately in this formalism. And it's because of all the decoupling that's happened. And then we are going to average over all of these. A lot of progress has been made locally, and we're going to then average over that. So this step here was actually in our original paper, what we proposed to do, so we could prove something about it. But it does slow things down, and then in a subsequent paper, we were able to turn that average into an ADDIE, which allows you to make a lot more progress and required a little bit more work. But the original paper had this averaging step. And so here is the overall method. This has now been implemented in a bunch of open source projects. So you will find it inside of Google software, and Apple has used it as it's implemented, and so on. But really, it's extremely simple. It's just a kind of naive parallelism where there's an adjustment of the dual parameters and the primal parameters on the local machine using any local dual method that you like. Then you adjust the dual variables there, and the reduce step is just to bring everything together and do averaging of the weight vector. Okay? I'll let you stare at that for a second. The kind of KKT conditions allow you to convert changes in the alphas to changes in the W's. So right here, if I have the alpha, the change in the alphas, I can turn that into changes in the W's, and I can go back and forth on the local machine between the primal variables and the okay, so that's COCO. Now, convergence. This is kind of interesting. What happens with COCO is that this particular upper bound function allows you to transfer any convergence rate you have for the local algorithm into a global convergence rate for the overall method. Right? So this is fairly strong. So if I'm using, for example, stochastic coordinate descent, you know, under certain assumptions, you can show that you make this much improvement per step, where H is a parameter of the algorithm. So like Peter Richter has papers that show this sort of thing. So this gives you linear convergence rates under certain assumptions, right? And the theorem that we're able to prove is that that transfers over into a global convergence rate for the overall alpha, where that theta here appears here, and then T is the total number of iterations. So we still maintain a linear convergence rate where the local parameter appears as a contraction. So let me sort of finish this part of the talk by turning to empirical results. These are relatively impressive. I think it's what convinced people to pursue this. So here are three particular data sets: ImageNet, RCB1, and COVE. You can see the number of training data points, number of features, and sparsity levels. And then we've done this with 4, 8, and 32 workers in these particular examples, and compared this to mini-batch SGD, mini-batch DCA, local SGD, and COCO, and kind of the features of the different algorithms that are given here. We have a Primal-Dual Framework. We have guaranteed convergence that inherits the local one. We're able to do updates immediately instead of waiting to synchronize, and then we can average, right? And so here is the kind of the original paper on this that showed these results that people, I think, found fairly striking, is that these are serious competitors that are widely used in large-scale problems. In terms of the criterion being the duality gap, COCO is significant. So that happens on a wide range of problems. That was ImageNet. Here are some of the others. COCO is serious advantages. And really what's happening here is that this is wall clock time. And the major advantage here is the lack of communication. Okay? So that is responsible. This is not convergence rate, and it's not amount of work per iteration. It's the lack of communication across the entire system. Okay, I think that's all I want to say on that. There was a little slide there. Right. So I have one other thing I can talk about based on some requests that was a little bit more mathy about matrix concentration. And I may turn to that, or I might just sort of see if there are questions about this. I could also just stop and have questions and discussion. So let's see where we go with this. Yeah. Yeah, so the original paper was only for the L2 norm, and then there's been 3 papers. The second paper switched the role of the primal and dual and was able to handle L1 as well. Yeah, that's right. We don't need speeds. All right, anything else? All right, so maybe I do have minutes. It's like 10 of them for this stuff, perhaps. So a couple of you, or several of you, came up and asked about this work here, so I think that there's some interest. This kind of revitalized, so Stein's method. So this is a part of a longer talk that I just snipped out here so I could tell you a little bit about the story. I don't have the authors here, but Lester Mackey, who was a student with me at Berkeley, this was his thesis. And Lester and I worked on it at Berkeley, and there was another team in complete parallel at Caltech, led by Joel Trop, who worked on this exact same idea. We came together and wrote a joint paper, The Analysis of Probability. And if you haven't heard of Stein's method, again, what I'm trying to do in my lectures is introduce you to things I think you'll want to know about that are a little off the beaten track. It's not in the standard machine learning textbooks. And Stein's method is definitely one of them. So part of the reason I'm doing this is because this is about matrix concentration, and you will hear there's lots and lots of good tutorials out there about just concentration of random variables, widely Bernstein and so on, but much less about matrices. And Stein's method turns out to do that. So first of all, who was Charles Stein? Charles Stein was a very, very famous statistician who died just a couple of years ago. Stein's shrinkage was due to him in the late 50s. Then a whole bunch of other ideas. He had a number of limits that kind of keep getting rediscovered again and again and again. A lot of them are kind of integration by parts kind of limits. And I have seen various neural network people rediscovering these and with different names in the context of, for example, ICA, seen these things discovered and so on. So, Stein did a few things, but he did them extremely well. And one of the things he did was he developed a new way to prove the central limit theorem, right, which is a pretty striking thing to do. There's about 6 ways to do it, and one of them is Stein's. The classical way to do it was basically Fourier theory, that you took the exponential of the sum of things, and you did Fourier theory on that, and you turned that into the exponential of something squared. You turn that into a Gaussian. So that approach, and then the Lindeberg method and all the other variations on that use independence extremely strongly. You have to have a sum of independent random variables. Okay, independence is needed to make that the characteristic function e expectation of e to the something factorize, and then it's work. If you don't have independence, not clear what to do. And so Stein got around it. And so what Stein did, which is kind of miraculous, is that he showed there's a certain differential equation on the space of probability measures, which is solved by the Gaussian and only the Gaussian. So if and only there's a certain differential equation, the solution is the Gaussian. That's already kind of interesting. So it's another character. There's many characterizations of the Gaussian distribution. That's another one. Right, but even more interesting, there's a metric in the space of solutions to differential equations, right? That is in one-to-one correspondence with standard ways of metricizing probability measures, weak convergence. Okay, and the link between these is something you may have heard of called Wasserstein distance. So what that meant is that you could take a differential equation of some kind, and you could take the one that the Gaussian solves, and then you could tweak that differential equation, to change it a little bit, and you get a solution to the tweaked differential equation, right? And that solution, if it's near in the original space, would lead to a distribution which is near in distributional space. Okay? So this meant that you could work out differential equations which characterized sums of random variables, which may not even have to be independent, okay? And show that their differential equation that characterized that sum was close to that of a Gaussian, right? And that is then enough to prove the central limit. Okay, without any independence assumptions whatsoever. Okay, so this kind of emerged. Stein never wrote this down in this way, but it kind of emerged over a few decades. And now there are whole books on Stein's method, which kind of set all this up. Right. So that's if you're trying to do distributional results. If you're trying to say, here, this collection of random variables that interact in a certain way are eventually going to be a Gaussian. Or then there's also versions that's per Poisson or other limiting infinite divisible random variables. So that is still very, very important in probability theory. It's used for example, if you're trying to show central limit theories results on graphs where the graphs have a lot of dependence. This is kind of the only tool program. Right now, at some point, people sort of say, well, could you use this for concentrations, not just for basic Stein method gives you the whole distribution, say a Gaussian. A lot of the kind of results we need in the more statistical fields, we don't care about the whole distribution. We just care about the tail probabilities. We can guarantee with high probability that some tail thing is not going to happen. And then, so this is the standard kind of argument you see in learning all the time. So can we just get tail probabilities, not full distribution? So the standard way of getting tail probabilities, concentrations, is large deviations, where you again use the exponential of lambda to the x. You take the expectation of that, and you use Markov's inequality, and you start heading down that path. And when you do that, if x is a sum of things, eventually you're going to have exponential of the sums of things, right? And you're going to have the kind of same Fourier, independence is going to be needed. All right, so
Saurav Chatterjee wrote a thesis about, I don't know, it's maybe 5 or 10 years ago now at Stanford, where he said there's a way of thinking about what Stein did for distributional theory, which you can apply immediately to concentrations and large deviations. And you can get concentration and large deviations rolled without any independence assumptions, right? And it's really easy. It's just elementary. And so you're going to get like a 2-page proof of concentration using Stein's method. Right? So it's one of the more amazing papers of all time. It's like 10 pages of just elementary calculations to get these very, very hard concentration inequalities that otherwise are hard. So we and others thought, well, does this allow us to solve some of the open problems in matrix concentration, right? Because in matrix concentration, so here's kind of been an open problem for quite some time, which is if you just look at scalar concentration, suppose I have a random variable x, which is the sum of a bunch of random variables I equals 1 to k of yk, and these are all yi. These are all independent. Then I would perform the characteristic function expectation of e to the lambda x, and then that would be e to the lambda sum over the yi's. And if these things are independent, I can pull the expectation inside and get a product, and blah, 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 blah. Okay? So Saurav sort of told us how to get around the independence issue, but now what if we're trying to do this with matrices? Suppose that this is a matrix. All these are matrices. This is a sum of matrices. Okay? So now independence we can get around, but we still are stuck with the following fact, that e to the a plus b is not equal to e to the a times e to the b. Okay? All right. Yeah, I'm not writing anything deep here, but there you go. Want to see it. All right. So unless these matrices commute, this is not true. All right. So the whole path of going down, of taking characteristic functions and breaking them apart and putting them back together, Markov's inequality and so on, is you stop, you're dead in the water. All right. So this has been viewed as an open problem for some time. Okay. So Lester got interested in working on this and started to work on this, and made a fair amount of progress. We kept talking about it. It looked like things would go, and there was a blockage point where it just couldn't, you couldn't get past this blockage point. And then Lester just came in our office one day and says, I figured it out. Right? So he was able to get past it. So this is a really, really nice major result. So I'm going to just give you a couple of highlights here. This shouldn't take all that long. I've kind of set up a lot of this already. What we're trying to do here is control over the probability that x minus its mean, that spectral norm or matrix norm, being bigger than t is small, kind of a classical concentration. So we might in particular focus on the maximal eigenvalue of the interesting x in it. Okay? There's lots of applications. All right, so the core problem is that matrix multiplication is not commutative. I can't do e to the a plus b is equal to e to the a times b. So there has been some work on this, and it's all very recent, that uses things like Lieb's result for matrix analysis. It uses matrix martingales, and it's highly restricted to the independent case, and it's let's say, somewhat complicated. All right, so what we've found is that you can apply Stein's method to these problems, that it all gets much more simple. You can get Hoeffding inequalities, Bernstein, Kinshin, Rosenthal, Bennett. You can get all those sort of things in an elementary way. So that's going to be pretty. So just a little notation. We're going to do Hermitian matrices here. The work is not restricted to Hermitian, but it just simplifies things. Maximal eigenvalue, trace, and spectral norm. I'm not going to need to keep. All right, so just a little bit of notation so you can understand what we're talking about here. So exchangeability, a key idea. If I had done Bayesian lectures, that would have been the main focus. Exchangeability just means if I have z and z prime and I reverse them, I get the same distribution. Okay, so it has the flavor of IID, but it's not IID. It's much deeper, much broader concept than IID. The order doesn't matter what that means. Okay, so now let's take our randomness z and our randomness z prime and put it through some function. I may not need this in some of the results, but let's, for full generality, let us have a deterministic function psi, and then the random vectors are going to be called x and x prime. So they're based on random variables z and z prime, which are not independent but are just exchanged. All right, and then we're going to define a kind of a shrinkage thing, which is that we say we condition on the z part, so that's this randomness, and we look at the other random object, and we want that to be close, where alpha is kind of a small number like 0.01, to x. Okay, so it's a kind of a shrunken version of X. All right, so one place this would come up is if you do have sums of IID things. All right, and X and X prime, let's suppose that X, let's go back to my example here. So let's suppose that X is like that. It's a sum of a bunch of IID things. All right, here's a way to form an X prime which is exchangeable. You randomly pick one of the indices from 1 to k. Okay, keep the sum of all the other terms, throw that one out, and throw in a new randomly chosen one, independently chosen. So I've perturbed X by a little bit, right? And it's kind of clear that these two things will have the same distribution, they're exchangeable. And it's also clear that X and X are very close to each other. And they only differ, in fact, by 1 over n, or 1 over k. All right? So alpha here would be 1 over k. They're close to each other with that factor. All right? So I'm trying to prove something about a concentration of a quantity X. The art here is I'm going to pick an X prime, which is close to X, and it's exchangeable with it. Right? So I have to kind of have a little art there. And in the IID sums kind of case, it's easy. If it was a graph case, I might take the same graph and I throw away one edge and I plop in a new edge. Okay? Things like that, little surgeries. All right. So that's the definition now of a matrix Stein pair. So they're clearly exchangeable, and it's obvious that they have 0 as well. All right, here's the other definition you need, and then we'll be done with definitions. This is going to be called a conditional variance. All right, so let's condition on one of the sources of randoms, the one associated with X, all right, and then take the expectation over the X prime part. Okay, so I have that expectation. If X and X have prime are exchangeable, so therefore they have the same mean, I could subtract and add back in that mean. The thing would break apart, and I would get twice the variance. It would be X minus its mean and X prime minus its mean. Okay, so this is a, and the 2 would go away. So this is a conditional form of a variance. Right? All right, so what we're going to be able to do is to show that if you can get control over this, that variance is not blowing up, then you can get control over the tails of your random matrices. All right, and that's very surprising. I'm claiming that just control over variance is enough to get control over all the tail probability. All right, and that is the magic. Yeah. Okay, so let me just show you, here's a theorem. And I will then show you a little bit about how we prove this theorem. Okay, so let X and X prime be a matrix Stein pair. So we're trying to prove things about X, and I then with some art figured out this X prime. All right, now let's suppose we can control the variance in some way. So what we could do is it's a matrix. So we control it by having an upper bound that has kind of a proportional to the random variable itself term plus another identity term. So the C and V are constants. Suppose that can be done, and I'll show you how you can do that for Bernstein, Hoofdien, and Rosenthal, and so on and so forth. If that can be done, you can get control the variance. Then we get a control on the matrix, the maximal eigenvalue of the matrix, and it looks like a Bernstein kind of form. Okay, it's less than or equal to e to the minus t squared divided by these terms. So if C is not present, if you had control without needing C, then you would get a sub-Gaussian result. Okay? It would look like a Gaussian. If V were not present, you didn't need that term, then you would get something, the T's would cancel. This would be a sub-exponential. So it's just like in usual Bernstein, it's a blend of sub-exponential and sub-Gaussian. Okay, so that is a general theorem. If you specialize that to sums of independence, that is not the focus here, but if you do, then the maximal eigenvalue of sums of independence has this kind of form, which is exactly a Hoofdien result, where sigma squared is each one of the random matrices has an upper bound on it. That's what you do in Hoofdien. You assume you have bounds on the random variable above and below. So we're doing that now in matrix land. And so you add up the bounds, right? So this result actually has a favorable other factor there, which strengthens Hoofdien. In fact, this strengthens the classical Hoofdien inequality even in the scalar case. Pretty interesting. Okay, so anyway, you form the sums of the bounds plus those second moments, add them all up, and that goes in your usual Hoofdien slot here. It's a sub-exponential, sub-Gaussian with that scale factor. Okay, this is a corollary of the result I showed you on the previous page. Okay, so I'm going to show you, I think it's a 2-page proof sketch here, and give you a little flavor of how these kind of things go. All right, so the first steps are ones that should be familiar to you if you've worked on large deviations at all. which are that you use, I don't think I need to write that out. How many of you have gone through large deviations and matrix, or sorry, concentration inequalities? Is that something? Not all that familiar, okay. Boucheron et al. Have a very beautiful book on concentration, which you should all also add to your reading list for the rest of the summer. Boucheron, Lugosi, and Massart. Very, very good thing to be reading. So if I'm trying to get the probability that x minus its mean, let's assume it's 0 mean, being bigger than t, is small, what the standard idea of due, I think, originally to Bernstein is that I'm going to take and multiply both sides of this by a lambda, which is greater than or equal to 0. So I haven't changed the event. And then I'm going to put in an exponential there, which is a monotone function, so I haven't changed the event. So I have equalities here. And now I'm going to use Markov. So this is going to be less than or equal to expectation of e to the lambda x divided by e to the lambda t. That's just Markov, right? And then I'm going to minimize the right-hand side over lambda. Okay, so I'm going to get that the probability of a fluctuation above some point of some random variable is less than or equal to the infimum over lambda of the moment generating function divided by e to the lambda t. And I can take logarithms here and get this into a sum. Okay? So those are the first steps of any kind of classical approach to concentration. Okay? So we are going to do something similar over here, and we will, by those same steps there, get that the probability of the maximal eigenvalue of x being bigger than or equal to t is less than or equal to infimum, I called it theta instead of lambda, of e to the minus lambda t from downstairs. And then m of theta is the moment generating function, but not quite. It has a trace in there. Right? And this is key. People in quantum information theory first wrote this down. Alsveda and Venter, they get credit for it, although it's kind of a triviality. Okay? If I didn't have the trace there, it would be just the same argument I had there. And we put a trace there because the trace is the sum of all the eigenvalues. So if we're trying to get an upper bound, and we want it on one of the eigenvalues, we might as well sum over all the eigenvalues, and we get a worse upper bound. Right? Now, that wouldn't be true if I didn't use the exponential there, because some of the eigenvalues could be negative and some could be positive, and I don't want to sum over the negative ones. That would ruin the bound. But because we took the exponential, they're all positive, and I can sum over them, and then I can get this upper bound. Right? So that's a key starting place, which means you look kind of classical here. You have the moment generating function, but using the trace. Right? So that's what happens in matrix land. Okay, now here is the key step here, which is that if you try to bound that term, you get into all the troubles of sort of statistical physics and quantum field theory and everything. You can't calculate these kind of things. It's an expectation of a trace of an exponential of something complicated. Hopeless. All right? So a trick, which is due to many, many people in many, many different fields over like 100 years, and Talleyrand has kind of made his life's ambition to make this as general as possible, is very simple. It's called the fundamental theorem of calculus, which is that you take that m quantity, which you can't work with very easily, and you say, let's write its derivative. Its derivative is easy to calculate. I take the derivative with respect to theta. I just get an x coming down, and then the trace, it's linear, so it stays there, and then I get e to the theta x. All right? Now, when you have the derivative of something, if I were to calculate that exactly, I could integrate it, and by the fundamental theorem, I could get m theta. Okay? All right, but the idea is that this quantity here is going to be much easier to bound and work with and control using probability tools than that one. And the reason is because this is, forget the explanation for a minute, a trace of one matrix times another. That's an inner product. And so in a Hilbert space, I can get control over inner products in all kinds of ways. Cauchy-Schwarz and blah, 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 blah. Kind of things we talked about yesterday. And the expectation is just a linear operator. It's not going to make life only easier. Okay? So if I can get control over some linear operators of inner product, then I can plug it back in there, and I can get control on that original. Okay, so that is the first key step here. All right, and the next key step is, I'm kind of running out of time, so I'm not going to be able to explain it too much, but it's very elementary, which is that suppose that x and x prime are a matrix Stein pair of the kind I defined earlier, and let's let f be some smooth function that has some kind of regularity condition. And so f for us in particular is the exponential of theta x. Just to be clear, we're taking the expectation of that times that. Right? Then you can rewrite this as an equality, and this is the Stein idea. This is what we borrowed from Saurabh Chatterjee. which is that inner product right there, can be written as an inner product between x and its Stein pair, x prime, and then f applied to those two things. All right, now why in the world would you want to do this? All right, well, because you chose x prime to be close to x by a factor alpha. And if f is smooth in this way, f of x will be close to f of x prime. That's true for the exponential. So these quantities can be made small with some calculus. And that will give you a tight bound on this quantity, which will then feed back into the bound of the original quantity. All right. So once you get here, you're nearly done. And this, however, was the point where we get blocked. We could not figure out how to do this for matrices. All right. So this is kind of summarizing where we are. We want this quantity, which is this derivative, and we're now rewriting it using that little argument on the previous page. This argument, by the way, is the core of the whole thing, and that's like a 3-line proof. And if I had had a lot more time, I would just go through it. It's just a Tower property of conditional expectation. Just easy as easy to be. Okay, so this is what we want to do. We've now kind of resumed the problem to that. And now we've got to get control on that thing on the right-hand side. All right, and this is where Lester came up with his brilliant insight. And his brilliant insight was this is really just like a mean value theorem, that in general, much more generality, traces of functions which are weakly increasing times functions whose derivative is convex can be rewritten in this way, where h, you put a derivative on it, and the minus becomes a plus, and then a minus b comes outside, and then the g part stays by itself. So I don't know how Lester came up with this, but it is a mean value theorem that sort of hadn't been discovered in the linear algebra literature, and it was precisely what was needed. So I think on this last page, this is the end of the argument. Here we have the first line that I've just copied from above. This next line is Lester's lemma, where that minus sign became a plus, and when the x minus x prime came out, and now you have two of them. All right? And now you simply just move that e to the theta x term next to that thing, and you get, by definition, that conditional variance we defined earlier in the talk. Okay? And because of exchangeability, you get two of them. These have the same distribution, so the factor of 4 is canceled by the 2 and by the definition of lambda, or sorry, of delta. Okay? So that's really just an elementary argument using Lester's lemma to reduce that quantity, which we're trying to get our hands on, to something that only has a variance in it and some function. So now we can get control of the variance in all kinds of problems in all kinds of ways. In particular, what if we assume the variance is controlled in this way? So plug this back into here, right? And you get Cx times this. Well, that's just m of theta times c, m prime. And you get I times this. Well, that's just the momentary function itself, times v. Right? So now we get a little simple differential inequality that any calculus student can solve. Okay? So you just solve that for m of theta. It's just a little differential equation with an inequality. It's trivial. All right? And that's the end of the proof. Okay? So that was fast, and I know you didn't get all the details or anything, but I hope you appreciate there was just a Tower property of conditional expectations, there was Lester's lemma, and that was it. And we're proving matrix concentration with no independence assumptions for a wide range of settings, which include Hufting, Bernstein, and so on and so forth. Okay? So I encourage you to read this paper. We spent a lot of time on the writing of this, and I think it's extremely readable. You would learn all this material as well as this result. So that's all I wanted to say about that. You can do matrix kinching with this and sort of all kinds of other things. So this has caught on a bit in the probability literature, but I think it needs to be understood more broadly. So let's see. Okay, so I am done. I went right all to 4 minutes after, and that was ended my 4.5 hours. I could go on for another 4.5 hours. I've been in the field long enough that I have lots of things I'm excited about. I didn't do anything Bayesian, by the way. I'm often associated with doing Bayesian. But I hope you get to appreciate, I picked topics that I thought if I were a student sort of in the 20 to 30-year-old age range that I'd want to hear about as kind of promising things to be working on, okay, that are not done, that are hard, but are not hopelessly hard. Okay? And if you make progress on them, a lot of people will pay attention to what you do, especially the kind of the gurus who understand these are kind of the hard problems that can be solved, but really some so a lot of it requires a certain amount of math, but not huge amounts of math. Just get good at your probability, get good at your optimization, and that will help you whatever else you do. So I'm happy to answer any other questions or whatever, but that was my attempt to educate a little. Yeah.
So in the bag of little bootstraps, you had this example. So once you get these, I guess, key values for each of the variables of
Confidence intervals.
How exactly do you use those settings? So many of them don't necessarily trust the details.
Great question. Yeah, so in some sense, I don't have a great answer to that. This is just kind of as an academic exercise to see if we could get them. But if I am doing a logistic regression on 100,000 parameters, probably I don't care about all those parameters. So a typical situation is that I've got a few parameters, kind of the causal ones, that I really care about. So one of the parameters is going to be, I gave you the drug or I didn't give you the drug, or the corresponding X will be that. I really care about that, the effect of that. Another one might be age, or there's going to be a few variables which have a semantic meaning to me, and I care about it, and I put them in there. And there's a whole bunch of others that I just measured because, I got data off the web, or I just have tons of other variables, right? And I don't care so much about them. So this is what's often called a semi-parametric setting. I'm doing the full analysis because I know I have all the data and I want to bring it in and then pull out the parts that I care about, and then I'm going to look at the confidence interval result. But that's just kind of one slightly unsatisfying answer. In general, if you had 100,000 variables, if you really wanted a confidence thing, it would be some ellipsoid shape in 100,000 dimensional space. It'd be very hard to think about that and visualize it and maybe use it. So you kind of have to think about, what do I really want confidence on? Well, I want confidence on the drug working on. So I have to say that marginal confidence is meaningful. And I didn't even do the extra work that should be needed to convince you the marginal probability of confidence. Actually, that would be an FDR problem. Okay, I'm done.